So today for the discussion, I chose I've chosen problem 10.17. And the question for this problem is right here. It says, a graph is Eulerian if and only if its adjacency matrix has what property? So, and this is it's a little difficult to put it into just one little paragraph, I guess, or one sentence. But a graph is Eulerian if and only if its adjacency matrix has what's property, which is an even degree. So it's basically just like if it has an even property. So just put for now, and then I'll explain it. So if it has an even property, so the definitions of terms that I'll be throwing in there just a little bit are the adjacency metrics, walk, trail, path, and of course Eulerian. So definition 10.57 is the adjacency matrix M of graph G is the n by n matrix. M defined as M quotation I comma J quotation mark equals, and then there's a 1 and a 0. So the 1 is if the 1 is for if I comma J is an edge, and then 0 is if ij is not an edge. So basically, what this is, what the adjacency matrix is basically if it just has an edge, which is connection between two letters, because that's what we're going to be using. Um, so definition 10.18, A U to V walk is an alternating sequence of vertices and edges in G with starting vertex U and ending vertex V, such that every edge joins the vertices immediately preceding it and immediately following it. Definition 10.19, a U to V trail is a U to V walk that does not repeat an edge. Definition 10.20, a U to V path is a walk that does not repeat any vertex. Definition 10.66, so recall that a trail is a walk where all edges are distinct. A Eulerian trail on graph G is a trail that traverses every edge of G. A tour of G is a closed walk that traverses each edge of G at least once. A Euler tour on G is a tour traversing each edge of G exactly once. That is a closed Euler trail. A graph is Eulerian if it contains a Euler tour. So right here, I'm going to show you guys Eulerian and not Eulerian, the difference between both. So this right here is a Eulerian, and the letters I chose, we're going to start from the beginning. So I put A connects to B, B connects to C, C connects to D, D connects to E, E connects to F, and then F connects back to A. So our vertices nodes are A, B, C, D, E, F, and our edges are A, B, B, C, C, D, D, E, E, F, F, A. And then in here you can tell from the beginning and the end, we come back to A. And then right here, I made my adjacency matrix, which up top for each row and each column, I did A through F. So it'll be A, B, C, D, E, F right here. And then going down, I did A, B, C, D, E, F. The way we get the numbers is from up here. So 1 if ij is an edge. So AA is not an edge. So that would be a 0. AB would be an edge because they're connected, so that would be a 1. AC, not an edge. They're not connected. And then so on and so forth. And right here in our adjacency matrix, you can see each time we did it, we got 2 1s, meaning that every vertex had an even degree, meaning it has an even number of edges connected to that 1. And that is how we got our graph for Eulerian trail, which is right here. And then now I'll be showing you guys a not Eulerian trail. So what I'm going to do is I'm going to erase this one. Back to typing. And this is going to change. So our vertices are the same, our nodes, they're going to be still A, B, C, D, E, F, but our edges change. So what's basically just going to change is going to be the last portion. So as you can see, the edges, we start with A, but we do not end in A. The reason for that being is because the edges connect A, B, B, C, C, D, D, E, E, F, but it does not connect F, A. So because it doesn't connect F, A, that's not an edge. And then right here, our adjacency matrix is actually going to change as well. So what's going to happen is for A, it's just going to change to, it's not connecting to F, so it's going to be 0. And this one will change to 1. Same thing with F. F does not connect to A, so that'll be a 0. And this right here changes to 1. And because these are not even, that makes this not a Eulerian trail. So back to our question, a graph is Eulerian if and only if its adjacency matrix has what property? And that's an even property. If it has even degrees for each edge, then it makes it a Eulerian. If it does not have the even degrees, then that makes it not a Eulerian. And that is how I got the answer for problem number 10.17. Thank you.